Corrosion and its impact on sugar quality in cane sugar industry. Abstract: in sugar industry, corrosion of process equipments not only causes increased expenditure on replacing worn-out equipments but also adversely affects the clarification process owing to higher color development due to reaction between iron and polyphenols. Experiments carried out in the experimental sugar factory of the Institute indicate mild to severe corrosion of mild steel in process liquors at different stages and a positive correlation between color development and iron content of the process liquors. Introduction. The menace of corrosion in sugar industry contributes significantly towards the national loss. With the growth and development of Indian sugar industry, at present 530 vacuum pan operating sugar factories and thousands of mini sugar plants, popularly known as Kansari sugar units, and in the absence of serious efforts to prevent corrosion, the losses owing to corrosion, dry or wet, incurred by the Indian sugar industry alone are estimated to be more than Rs 500 million per annum. In a sugar factory, most of the process equipments are operated at elevated temperature, higher hydrostatic head, higher flow or circulation rates, and either in acidic or alkaline medium. Due to continuous use under such operating conditions, the wear of equipments increase gradually due to corrosion and erosion, and after some time it becomes essential to replace it so as to avoid any mishap, breakdown and consequential losses. Further, since iron content of the process liquors, besides certain other factors, is very much dependent upon the corrosion rates at various stages, higher corrosion rates due to one or other reasons, may enhance color development owing to its reaction with polyphenols present in the process liquors. The present study has been carried out with a view to ascertain corrosion of mild steel at various stages of processing and also to determine possible quantitative relationship between iron content of the process liquors and color developments during manufacture of sugar by double sulfitation process. Review of literature. In advanced countries, 1,2 efforts have been made to identify the causes of corrosion and steps have been taken to minimize it through research and development. However, in developing countries like India, due importance has not yet been given to control it in proportion to the magnitude of the problem. Like many other chemical and food processing industries, sugar industry also encounter the problem of corrosion. Many equipment or their parts wear out under operating conditions and necessitate frequent replacement. Scientists from various countries, 3 to 7, have reported the corrosion problem station-wise in cane sugar manufacture and suggested few preventive measures also. Vyzalkova et al. 8 and Kukita et al. 9 in their study found that corrosion resistance of various equipments can be improved by applying various protective coatings. In an interesting study, Sethi et al. 10 found a definite relationship between color value and iron content in a given grade of sugar manufactured by double carbonation and double sulfitation process. Material and methods. Preparation of specimens. Rectangular samples of mild steel were cut to identical size and drilled at the center of the upper edge so as to have suspension holes of mm diameter. Final surface treatment included finishing with 0, 0, 0, and 0, 0, 0 grade emery papers. These specimens were abraded first in the lengthwise direction, then across the width, and finally using a circular motion. The specimens were wiped with cotton soaked in acetone and dried. Experimental. The experiment was carried out in the experimental sugar factory of the Institute to ascertain rate of corrosion of mild steel at various stages and to determine iron content and color values of process liquors at various stages of processing. In the process, composite samples of mixed juice, clear juice, filter juice, unsulfured syrup, sulfured syrup, and final molasses were analyzed. For determining intensity of corrosion at various stages, 3 specimens of mild steel were exposed for 72 hours in relevant process liquors. Prior to weighment of specimens after exposure, they were rinsed for few seconds in running cold water and the adherent corrosion products removed by hard brushing and immersing in distilled water. Analysis of process liquors. The composite samples of relevant process liquors were analyzed using AR-grade chemicals of Merck/Ranbaxy and A-class glassware of Borsoil/Venzel make. The process liquors were analyzed for various parameters as per the prescribed procedures of ICMSA, International Commission for Uniform Methods of Sugar Analysis, UV-vis spectrophotometer, model UV 2600, electronic weighing balance and microprocessor-based digital temperature and dew analysis kit were used during the analytical study. Results and discussions. Data pertaining to experiments conducted for determining the intensity of corrosion has been recorded in Table Number 1 and average corrosion rates of mild steel in different process liquors have also been presented in Fig. 1. From these tables and Fig. 1 following observations can be made. Corrosion in mixed juice. Data with regard to corrosion of mild steel in mixed juice has been reported in Table 2. It is evident from the table, corrosion rates of mild steel in mixed juice are around 1000 mg per decimeter square per day, MDD, which are appreciably higher than the corrosion rates of mild steel in any other process liquors. It may be primarily due to lower pH values, 5.1 to 5.3, higher dissolved oxygen content, 53.7 to 6.2 mg/liter, and significant amount of suspended solids present in mixed juice during the experiment, Table 1. Corrosion in sulfite juice. It is evident from the Table 2 that mild steel corrosion is lowest in sulfite juice amongst all other process liquors barring unsulfured syrup and final molasses. Although the temperature and dissolved oxygen content of sulfite juice being in the range of 68 to 72 C and 3.2 to 3.9 mg/liters respectively are liable to increase corrosion rates, but the pH of sulfite juice being around neutral, 6.9 to 7.1, may be the main factor restricting the corrosion rate. Corrosion in clear juice. Apart from various other parameters e.g. pH, dissolved oxygen content etc., it is the temperature which influences the corrosion rates. Since the temperature of clear juice remains much higher, 94°A95 C, than any other process liquors, the mild steel corrosion was observed to be appreciable. The pH and dissolved oxygen content of the clear juice was found to be around 6.7 to 6.9 and 1.8 to 2.0 mg/liters respectively. Corrosion in filtered juice. Mild steel corrosion was found to be considerably higher, i.e. around 800 mDD, mainly due to lower pH and higher temperature of the filtered juice. It can be observed that mild steel corrosion rates in filtered juice are higher than those in clear juice and somewhat lower than those in mixed juice. Moderate quantity of dissolved oxygen in the filtered juice also contributed towards higher corrosion. Corrosion in unsulfured syrup. A perusal of the data contained in Table 2 reveals that mild steel corrosion was determined to be much lower, around 150 mDD only, than corrosion in other process liquors. The main reason for such behavior may be due to higher solid concentration, Brix % 55 to 60, and pH approaching neutral, 6.5 to 6.7. Corrosion in sulfured syrup. In a sugar factory, prior to crystallization, syrup obtained from evaporators, i.e. unsulfured syrup, is bleached by passing SO2 gas, and in the process the pH of sulfured syrup is maintained around 5.0 to 5.2. The corrosion rates of mild steel in sulfured syrup were found to be around 375 mDD, which are almost 125% higher than the corrosion rate of mild steel in unsulfured syrup. Since, as evident from Table 1, except for pH, there is no material change from unsulfured syrup, it may be inferred that corrosion rate has increased owing to lower pH values. Corrosion in final molasses. The data obtained with regard to mild steel corrosion in final molasses has been presented in Table 2. It can be observed from the table that corrosion rates in final molasses are considerably lower and comparable with those in unsulfured syrup. Such behavior may be attributed only to the higher total dissolved solid content, 85 to 87%, of the final molasses. It is accepted that at such a high dissolved solid concentration, the quantity of dissolved oxygen, which has prominent role in corrosion, will be very low. Further, an experiment was conducted in laboratory to precisely ascertain the increase in iron content in juices owing to corrosion and color development due to reaction between iron and polyphenols. In one set of experiments, samples of mixed juice collected after regular intervals were clarified in the usual manner, i.e. using mild steel vessels, whereas in another set same sample of mixed juice was processed in glass vessels. Samples of mixed juice and resultant clear juice were analyzed for iron content and color values in a manner described by IJERT. The results of the experiment are given in table No-3 and also presented in graph, Fig.2. Data presented in table No-3 and Fig.2 indicated that for a given quality of juice, keeping other variable constant, the iron content is more in the juice which were processed in mild steel vessels than to the juices processed in glass vessels, and so is the color development. Thus it may be inferred that the formation of coloring compounds as a result of reaction between iron and polyphenols may alone increase the color values of clear juice by 5 to 7%, which in turn on crystallization may enhance the sugar color by corresponding value. Conclusion. On the basis of studies carried out, it may be inferred that the mild steel process equipments in sugar industry suffer moderate to severe corrosion depending upon the characteristics of process liquors. In general, low pH, below 5.0, temperature, above 70 C, higher dissolved oxygen, above 5.0 mg/liter, and lower dissolved solid content, below 40 brix, of process liquors enhances corrosion rates. Further, there is a definite relationship between iron content in the process liquors and ultimate color development. Since corrosion increases iron content in the process liquors which reacts with polyphenols present therein, it is expected that there will be substantial color development owing to this reaction, which may alone increase the color values of sugar by 5 to 7% or even more depending upon the iron content and polyphenols present. As such, preventive measures need to be taken to minimize corrosion of process equipments at various stages so as to restrict iron content of process liquors.